Good morning, everyone. Good morning. This is EE4800 Senior Design Team A. The team would like to begin by giving exceptional gratitude to Universal Alloy Corporation for sponsoring this project. Also, a huge thank you goes to Texas Instruments for sponsoring many of the materials that are used and make this project possible. A great deal of gratitude also goes to Dr. Okayo, Dr. DeYoung, Dr. Cheng, Dr. Tekis for all of their guidance and expertise. The objective of the project was to design, build, and test an electrical and thermal conductivity testing device for aluminum extrusions. The image below on the screen shows the main integral components that are used to make the project work, including a printed circuit board with all the major components, including a microcontroller and the function generator to the right. Each of the individual responsibilities of the team members are listed here, anything ranging from and coordinated to circuit design and analysis, 3D printing, and microcontroller programming.
Universal Alloy Corporation needs to test its aluminum extrusions to see if they've been properly heat treated. The importance of this is to make sure that the aluminum extrusions increase the properties of the aluminum. Currently, the equipment used for testing the alloy of the temperature does not take into consideration the alloy temperature when making its calculations. Also, the ambient temperature must be periodically remeasured, which increases the time of the process as well. Here is shown heat treatment, or the steel going through the heat treatment process. An example of this importance can be seen in airframes. The aluminum alloys used in building airplanes must go through proper electrical and thermal conductivity tests to verify the strength and integrity of the aluminum. Currently, the current method is the most efficient process for conducting electrical conductivity tests, although it does leave several areas for improvement. The goal of this research is to minimize the risk of human error while also to increase the efficiency of the process by automating the electrical and thermal conductivity evaluations.
So, the fundamentals of this project is that there is an inductive coil that, when the current is ran through it, generates an electromagnetic field. And once the electromagnetic field comes in contact with the aluminum extrusion, it induces an eddy current. Once the eddy current is picked up by the sensor, the analog data is then converted to digital data by the microcontroller and is processed by the microcontroller for the conductivity calculation. Here is a diagram that shows example of the coil and the electromagnetic field going to the material and creating the eddy current.
When conducting these calculations, the ambient air temperature and the extrusion temperature must both be taken into account. This is due to the inverse relationship between temperature and conductivity, so both of those have to be played in, especially for the thermal conductivity component. The thermal data is going to be measured by an infrared thermopile with I2C compatibility. The sensor can make measurements in real time and constantly update itself to provide proper data to the microcontroller for calculation. The calculation programming is written to incorporate what's known as the Wiedemann-Franz law, which states the relationship between thermal conductivity and electrical conductivity. The image at the bottom of the screen, down here, is a formulaic expression of the Wiedemann-Franz law, where K is the thermal conductivity coefficient, sigma is the electrical conductivity in Siemens per meter, L sub 0 is Lorentz number, which is a constant and is equated to 2.44 times 10 to the negative 8, and T is the varying temperature of the extrusion, which is the variable in the equation. Depicted in these images are both a physical circuit and the circuit diagram. In regards to the circuit diagram on the right, the three terminals over here on the right-hand side are where power is supplied to both the inductive coil and the infrared thermopile. At the same time, this reads in data to the LM339 comparator chip, which will then take the average voltage that is supplied and read in and send it to the analog to digital converter, which is this column right here. And when the analog to digital converter converts that analog signal, it attaches it to an I2C bus shown here in purple. Also attached to that I2C bus is the data that comes in from the infrared thermopile. The microcontroller, which is this large column on the far left, can actually read in both of those specific addresses from I2C compatibility and perform the calculations necessary.
This project used 3D printing for the design for economic efficiency and ease of use. The 3D components, printing components, are the probe handle and cap that holds the eddy current sensor and infrared sensor, the BNC holder to hold a coaxial cable used that sensor, the SIMD case that holds the function generator and the circuit, and the graph that holds the ambient probe temperature that measures the ambient temperature of ambient.
So, the Node MCU microcontroller that controls the conductivity meter can be easily programmed by using Arduino IDE. Arduino IDE is open source software that can make it very easy to write the code and upload it to the controller via USB. This code can be broken down into 4 main parts. First is the libraries. Libraries is already written code that can be downloaded from various websites to the Arduino environment and then be used cold when they need to be used. This library specifically contains the code that will help us to control the sensors. Second is the variable declaration. These variables will be then used later in the calculations. The third part is the setup function. The setup function contains .begin line. This .begin will set up the communication between the microcontroller and the serial monitor. The serial monitor will display the all gathered data that will be collected from the testing. And then the last part is the main loop. This loop is set up to continuously run our gathering of data and then calculating electrical conductivity, thermal conductivity, and the value percent of IACS of the material. And then you will send to serial monitor for the user to be displayed for the user and then be used in further analysis.
This table shows tabulated data that was collected during testing. During testing, multiple points were tested on the extrusion so that relative data could be compared with calculated results. The main points of interest within this slide are the object temperature, the electrical conductivity, and the thermal conductivity. These are plotted results that were obtained during testing. These plotted results show a proportional relationship between the temperature of the object and the thermal and the electrical conductivity. This proportional relationship shows that as the temperature of the object increases, the thermal and electrical conductivity therefore decreases. This data is in line with our theoretical calculations that were made. The following video shows the calculations or the data that was obtained during testing.
Explain what it is.
As you can see within this testing, multiple points were taken from one end of the extrusion, moving inward. The computer shows data changing within real time.
In conclusion, in the past, both electrical and thermal conductivity testing has been performed by hand using different methods, and this has become inefficient on multiple grounds, including cost, time, and materials. So the previous research done determined that the most effective method for electrical conductivity was the eddy current method. This knowledge has been incentivized by using the analysis of including the thermal component to make a more accurate real-time variation compensation. In order to expand upon these factors, the project was to design the automated system for measuring eddy currents and the component temperature in the aluminum extrusions to determine the electrical and thermal conductivity requirements. Please take a moment to review the references. Thank you.
First and foremost, big thank you to TI for sponsoring all the equipment that was used, the MM-Wave sensor and the microprocessor. Without them, this could not have been achieved. So, okay. So the project is the designing, building, and testing of a smart traffic light control device. The group members are displayed up here. We have Daniil, Sam, myself, Troy, Matthew, Albert, and Samuel Lee. Ultimately, the project motives behind building this smart traffic light device is traffic. There are vehicle buildups that occur at intersections and traffic junctions, and it's due to a lack of good and efficient traffic detection equipment and non-dynamic traffic timers. Although we have current systems that have their effectiveness, there are drawbacks to each system. For example, induction loops and CCT imaging are very costly, hard to install, and have inefficiencies in them.
So the most important device in the Smart Traffic Light Control Systems project is the millimeter wave radar sensor, the IWR1642 boost. Radar systems operate by emitting an electromagnetic wave known as a chirp, and having that chirp travel some distance to an object and return back to the radar sensor. The radar sensor is then able to calculate a few things about the object, such as its speed, size, angle, and by comparing the original chirp to the reflected chirp. In the case of the IWR1642 boost, the wavelength is about 4 millimeters, and due to that small wavelength, the electromagnetic waves are able to pass through enclosures around it, meaning it's possible to protect the radar from the elements, as well as the fact that the inclement weather elements do not adversely affect the radar. When combined with a microprocessor, the radar sensor is able to track traffic influxes, make changes to the traffic light accordingly, such as changing a red light to a green light, setting a green light at the appropriate time for the appropriate number of cars, as well as extend the green light time as more cars approach.
The theoretical design of the approach is a MM-Wave sensor coupled with a microprocessor, and this is connected with the RJ45 pinout, which is known, which is known as an Ethernet port, and this is connected to a traffic junction box, which ultimately makes the changes to the traffic light. And this is all also connected to the grid, and that is how it's powered. The goal is still to make a lightweight and very cost-effective alternative device using multi-millimeter wave technology and high frequency. And the multi-millimeter wave radar sensor should interface with the microcontroller, and that is how information is conveyed, such as target count, which will be gone into later.
So, as proposed by the idea of the project, using the MM wave as a way to reduce the flow of traffic, and also within a certain time frame is able to reduce the carbon emission of the vehicle, and also do as to as being protected within the property is not going to be affected with the outside element. It's also have a longer lifespan, and also because of its use of less power. Use of less power is better. It's considered to be better for the environment, and also because of use of less electricity, and because of the MM wave radar is being so small, it has the advantage of disposal of less, and also compared to other sensor out there, is considered too big and take up space.
Project economics. One of the challenge is to make sure everything is low price. As you can see right here, the induction loop costs between $2,000 to $3,000, which include labor, and the estimated radar and CCTV cost is between $5,000 to $7,000. The price breakdown right here is $299, which is the MM wave given to us by Texas Instruments. Also, the microprocessor given to us by Texas Instruments, and 5-volt power supply, which is $4, and DC power plug, $5, and some screws. The total price is $335.95. Compared to induction loop, radar, and CCTV, by far this is the cheapest and the easiest way for traffic control system.
Here are the results that were found from the experimentation and testing. In the top left corner, there's a setup of a power brick powering the radar, and the radar is also connected to the laptop that runs a MATLAB GUI that will display the current setup of the traffic intersection. As you can see, this shows an XY plane of the 2 detected cars that are shown there. Also, the GUI shows the target count as 2 as well. These 2 images here show a protective casing that was 3D printed to protect the radar. And this is what it would look like in a traffic line. To the left, there's a flowchart that describes the program's operation. Starting from the top, it starts as a red light, that's the initial condition, and it reads the detected cars from the PC, and it asks, is it greater than the minimum number of cars to switch it to green? If not, continue to read the number of cars. If yes, then switch to green light mode and wait the minimum time and detect the cars from the PC. Then ask, is the detected cars equal to 0? If yes, go to yellow and then red and start the process over again, because there's no need to extend the green light. However, if the detected cars is greater than or equal to 1, then the elapsed time plus the extra wait time is greater than the max allowed time. Then you will wait max time minus the elapsed time, because that's the capacity, the full capacity of the time allowed. And then it'll go to yellow and then red and start the process over again. However, if it's not reached the max, then it'll continue to detect cars and run that green light operation again. In the top right corner, the picture shows what the setup would look like. The radar is connected to the PC, the microcontroller is connected to the PC as well, and the microcontroller has GPIO ports that allow you to power the LEDs that represent the traffic lights. Here's a video demonstration of this. There's 2 cars coming down this parking lot. As you can see in the top right corner, there's the red, yellow, and green, and the GUI in the bottom right corner. The car will drive down, initiate the green light, and start the minimum timer of 10 seconds in this case. Because another car is coming down, it will extend that time by an additional 5 seconds. So we see that there's 15 total seconds, causing it to go to yellow and red.
The MM mmWave sensor has great potential to reduce traffic control. Control. It integrates well with a microprocessor, which produces a small form factor device, which is very small, and said before, can be protected by weather. But most importantly, mmWave sensor can detect vehicles from 35 to 40 meters away. And that data is what will be used to, as I said before, control and improve traffic congestion. There are a few issues. The sensor has trouble detecting consistently small vehicles, especially when there's larger vehicles in front of it. Since the sensor senses everything in a 2D plane, and the large vehicle will block the small vehicle. As well as the sensor can be inconsistent during startup. However, all these problems are software problems and can be easily solved with more research and future work. The research is going to be done in the software where the sensor will start up on power on instead of when you start the GUI, as well as improving the consistencies of the device when start up. The other research that can be done in the future is allowing the programming the config file to detect both small vehicles and slow vehicles with low velocities, because low velocity currently with the config file, it considers low vehicles as stationary objects around the sensor. You can also develop a serial peripheral interface where you can send the data directly from the sensor to the microprocessor without having to go through a CPU as currently used.
As previously stated, a big thank you to Texas Instruments for sponsoring the project. The fact that we were able to use such groundbreaking and impressive equipment is nothing to scoff at. We'd like to thank the members of the EE department faculty for assisting us throughout the entirety of it, as well as specifically Dr. Okayo, who met with us on a few weekends to help drive cars around, as well as to actually purchase the radar sensor for us after a shipping error. Here's our biography. Are there any questions?
If you change the wavelength.
Good morning. This is Senior Project Group C. The project is to design, build, and test acoustic MIMO multiple input, multiple output, or MIMO test bed. These are the members of the group. I'm Aaliyah Canteen.
I'm Molly.
I'm Sammer.
Nikki.
Eugene Bond.
The background for acoustic massive MIMO. On the receiving side, a microphone array uses delay and sum beamforming to listen in a particular direction. And on the transmitting side, a speaker array uses constructive and destructive interference to sum signals at points of interest. Beamforming is also a key component of 5G cellular communication. More background information. The project is based on a project that was done in 2016 at a Linköping University, which is in Sweden. They use labor-intensive and custom-built parts. For this project, we're going to use off-the-shelf components, and it's an attempt to achieve results from Linköping University, and that could be reproduced by any group.
So the motivation of doing a project like this, Massive MIMO is a emerging technology that's being used for improving wireless communications in a lot of ways. It can communicate with many terminals on the same frequency, so that increases the data rate while reducing the power consumed due to array gain. Also another possibility for use of MIMO is redundant transmission, which so transmitting the same signal on two different channels, which can be used to reduce error and increase signal reliability. Acoustic MIMO specifically can allow for two different simultaneous audio transmissions from the same speaker array. So some marketable examples of this are like a television or display that can broadcast two different soundtracks to two different people standing in front of it. And the motivation of this project specifically is to create a test bed that is adaptable and can be reproduced easily that will allow for faster progression of research in this area. Do you want the microphone?
The hardware section, the selection in this project is basically on audio injector octo that perform analog, convert analog to digital signal or digital to analog signal. Using octo is necessary, basically require Raspberry Pi over some solution that was basically available. In this project is pretty much try to set up six input and 6 output signals. So basically the project was based on transmitting four different using 4 transmitter and 2 receiver. So the speakers basically was choose arbitrary based on the specification of the one the groups choose is pretty much have 8 ohm and 96 dB. The microphone chose for this project was the Maker Hack electret microphone. This microphone was chosen based on the sensitivity, the high sensitivity and the low cost. The build material basically elaborate the cost of the different component that was used for this project. So the total pretty much, that was set up for this project is about $183.51.
So the idea with what we would do with this hardware is that since the octo sound card we chose connects to the Raspberry Pi, it would be easiest to play and record the audio data from the Raspberry Pi. So in order to do that, we use the MATLAB Raspberry Pi hardware library was used, and it connects to the Pi via Secure Shell SSH to transfer data and execute bash commands. And the ALSA API is what is used to record and play sound on the sound card, and the signals, the WAV files, are saved to the Pi's SD card and can be accessed by MATLAB over SSH. So this is the idea of how the software is to work. So the setup is the Pi is turned on and the sound card is verified that it is working, and the MATLAB program is started. It establishes connection with the Pi, and then the first step of the procedure to establish the channels is a pilot signal is sent and played from the receiving side, which is why there needs to be speakers and microphones at each terminal, receiver and transmitter. So the receiving side plays a pilot signal, which is recorded, and digital signal processing is used to determine the channels, and then the phased signals are generated to beamform in a specific direction, the 2 directions of the receivers, and then that is recorded and played back, or checked for verification that it worked.
Some challenges that were faced for this project was first the hardware. The first octo sound card that was given to us, was given to this group, was dead upon arrival, and it had to be replaced. The speakers were unamplified, so the sound that was being transmitted was very, very low, as well as the microphones were unamplified and unable to really pick up any sound. That caused for small signals, and amplified microphones as well as speakers were necessary to improve this project. For the software side, the Linkoping project source wasn't available to this experiment, and the amount of programming effort was underestimated. The beamforming of the audio on the transmission side was more challenging than expected, and that could not be achieved. For the results, this project system was assembled. The 6 speakers and microphones could be used for arbitrary playback from the Pi and the MATLAB. And the MATLAB code for the beamforming microphone array could also be performed. The feature parity with the Linkoping project was not yet achieved. For future work, this project would hope to elaborate on the MATLAB program to pilot a signal for calibration. Also, in hopes to use a QPSK encoding and decoding, and to test improvements to the beamforming algorithm in hopes, using zero forming. As I stated before, the hardware improvements, more speaker microphone pairs would also be necessary as this group, adapted the Linkoping project. Some concluding remarks. This project was to expand on the Linkoping project, reducing the complexity and the cost, which would be economically important, as well as to improve the signal-to-noise ratio, the speed of transmission, and the reliability of the transmission. Using recycled parts with sustainability in mind, and for the future students at Kennesaw, this project would hope to be, adopted by them and hopefully turn into something better. The motivation for this project was to provide a better understanding of fundamentals for next generation communications that was stated earlier in the project, like 5G. These are some references, and I'd also like to take the time to thank Dr. Okayo as well as the electrical engineering department for their hand in this project.
Well, hello and welcome to Group D's presentation of the Bluebird Snake Deterrent. Before we begin, I'd like to make some acknowledgements. First off to Texas Instruments for donating all of this technology for students here. Also to Dr. Okayo for all of his advice and how to go about getting this together. Also to Dr. Lee for being our faculty advisor and putting up with this for all of this. I'd also like to thank Assistant Professor Gundre Parker, who is not able to be here. She is the assistant professor with the biology department and helped us with how to deal with snakes. We would also like to thank from the American Bluebird Society, Mr. Gunn and Mr. Rector. Thank you so much for bringing this to us. So, Group D, to design, build, and test the Bluebird Snake Deterrent. My name is Brian Langham.
Daniel Lee. Rob Chang.
My name is Guitang Nguyen.
And I'm Amber Dawson. A little background. Bluebirds are a success story for wildlife management, but just because they have been removed from the endangered species list, that doesn't mean that they're not protected. Their main predators are house sparrows, raccoons, and primarily black rat snakes. And for this, black rat snakes will be the predator. The task is to design, build, and test a deterrent apparatus that could be attached to the next box pole of various types to discourage snakes predation. The design parameters are as follows: inexpensive, scalable, visually appealing, solar powered, and non-lethal. The reason for the project is because snakes have a habit of climbing up into the next box poles and eating everything that is inside. Also, they can stretch to half of its overall length on the pole.
They have similar electrical potentials to that of a human skin, and they have a predatory instinct that is unlikely to be distracted by anything less than an electric shock. Here are some previous designs that exist. As Mr. Schuler was explaining, this first design, it works, but the snake can go over this instead of going inside of the box and nothing will happen. For this design here, it works for everything besides the snake. This design is just scalably too big, and if the snake get caught in this net here, then the question is what happens with the snake?
So, once again, to reiterate, areas of focus for this project are to be non-invasive, non-lethal deterrent, a cost-effective and economically viable solar solution to minimize design and make it as user-friendly as possible, to be weatherproof and sustainable for longevity. So, this can be broken into the three portions: design based on review of literature, the build consisting of 4 components, the solar charger and battery protection, the control unit, discharge circuit, and housing. A variety of tests were planned, such as runtime, ramping discharge, sustained maximum discharge rate, and extreme weathering. Here's a block diagram of the design overview. Portion 1 is the solar circuit along with battery protection. Section 2 is the discharge circuit, and Section 3 is the computational control, which is BeagleBone Black. On the bottom here, you can see the solar circuit, the battery protection, the batteries themselves running to a MOSFET, running to the discharge circuit. Infrared beaming was used in order to detect any snakes climbing the pole, which was caught and recorded by the BeagleBone Black, sent to the MOSFET, and then activating the discharge circuit.
As for the actual discharge circuit, the project required a non-lethal shock deterrent. The project came down to the project required a transformer that was a high in voltage but low in current, so that there would be enough power to actually arc between a small gap as well as be non-lethal towards the predator itself. The project came up to a small, low noise, 30 kilovolts, 50 kilohertz transformer, which is displayed on the slide right here, with the wires towards the output. And the next slide, this is where the project actually came to its final form, whereas the project was tested by using copper plates with a small air gap of less than 1 centimeter to physically show and give off a spark.
This is the code for the BeagleBone board project. The pinouts are set up here. The set interval is a built-in function for the BeagleBone, which calls the check PIR every 1 second. The check PIR function checks for each IR sensor, and then its parameters sends it to print status function. The next function, which is print status, determines if the LED or if the IR sensor has been triggered or not, and then turns on the LED. And then it displays a broken or unbroken message, and it sends a counter.
So using existing patented design and existing birdhouse dimension specifications, this is the design that the Group D decided to design that would be most ideal and realistic. The two compartment would be the top part would be to house the computation control section, and the bottom part would be where it would house the discharge circuit, and then it would. And then it would be separated to prevent the electricity in the wire from interfering with the host. And then with that, we applied the component onto a physical model presented to us by National Bluebird. And then this is the breakdown of the materials that were used. The majority of the costs went through the BeagleBone Black. A second thank you to Texas Instrument again for funding us the part. And then putting the whole project together, the initial goal was to build and design a cost-effective, non-invasive, and a aesthetically pleasing model. The challenges that the group faced was working with such a high level of voltage that it malfunctioned a lot of our electrical components. And the other challenge was setting up a connection between the control module and the discharge. But through that, the successes that we've gone through is establishing a stable code that would manage and output the discharge unit, and establishing the relationship between the control unit and the discharge unit. And then the breakdown of our schedule, breaking it up into 3 phases of planning and initiation, execution, and closure, with the bulk of the focus being around planning.
So, in conclusion, this project has hoped to provide an alternative to the National Bluebird Association for deterring black rat snakes. In repetition, high voltage is being used with lower current in order to apply a non-lethal shock. And also to reiterate, snakes are incredibly persistent, and this design has been tailored specifically for their biology and patterns of behavior. This snake deterrent fulfills the roles of being non-invasive, non-lethal, sustainable, and weatherproof. This design project could be expanded by setting up this build for production by creating PCBs, cutting costs by simplifying design, having Wi-Fi connectivity, and engaging in better shielding and yes. Acknowledgements again. Thank you for your time.
Hi everybody, we're Group E. I'm Garrett.
I'm Kaz.
Kyler. Brent.
Kenny.
Our project was the design, build, and test of a wearable blind spot detection system for cyclists and pedestrians. The problem is that runners and cyclists alike both use headphones and music when they're exercising. According to a study conducted in 2016 by Runner's World, 61% of these endurance athletes listen to audio while they run or cycle. On instances on shared use paths, which is a path where bikers and runners can use the path at the same time, a runner might be running with audio on, and they may not hear that a biker is approaching from the rear. This can possibly lead to a collision and an accident for both the runner and the cyclist. The proposed solution was a wearable blind spot detection device that can alert the user of approaching objects. It uses the fundamentals of ultrasonic sensors to calculate and measure the speed of the approaching object. It's to be worn while exercising and will provide an audible response once the detection algorithm makes a decision. And the device can analyze changes in speed and defines a certain level of danger based on that speed. And each danger level corresponds to a specific colored LED.
If we look at figure 3 over here, the detection algorithm is explained in detail. At startup, a pin configuration service runs on a script to automatically configure every single GPIO pin utilized. It sets the polling mode and the initial value. At this point in time, the ultrasonic sensor will also begin taking distance measurements, which will then be fed into an analog input pin on the BeagleBone Black. Using the BeagleBone Black's integrated ADC, the analog voltage levels that are being read will be converted to digital values, which then can be used to calculate the distance. Based on a counter, the now digital values will be converted to actual distance measurements and stored into either one of two variables. These two variables are then used to create to calculate a delta measurement. The delta measurement will essentially just be the distance difference between two distance measurements if they're getting closer or farther away. Based on that, danger level is determined. As soon as we have a danger level determined, different LEDs will be lit and buzzers will be sounded when needed. This entire process is repeated every single 100 milliseconds as the ultrasonic sensor continues to read in new information.
So, this project design has a few hardware components. The entire device is being powered by a 3.7 volt lithium-ion battery. The ultrasonic sensor feeds analog input into the BeagleBone Black Wireless, which is a single board computer. This is read through the analog in and is converted to digital, and then is sent through the detection algorithm and sent back as an output through the GPIOs to the buzzer and different LEDs. This is the breakdown of cost. We have the Maxbotics MB1260 ultrasonic sensor, the BeagleBone Black Wireless, the resistors, LEDs with PLA filament for 3D printing. Also, we have the lithium-ion polymer battery, which is 2,000 milliamp hours, and the total was just over $150.
So the enclosure design had a few constraints in which all of the electronics had to fit in and be fairly snug, as it would be on the back of a runner, so there would be some jostling. And it had to fit into a runner's pouch, which is essentially a slim fanny pack. And the sensor and buzzer for this instance need to be on the outside of the runner's pouch. So the design that was implemented actually uses these screw-on caps to lock two doors into place that are on hinges. And all of the components are inside, very snug, and these caps allow for screwing onto different thicknesses of material on running pouches.
The impact of our final results include a very dependable sensor that reads within 2% of actual distance, a lightweight device that can be easily carried, which would appeal to consumers. The buzzer has a very ample amount of audible volume that is capable up to 100 decibels if fed 24 volts. In our case, it's fed about 3. And also, this problem isn't very well known, and there's currently not a product like this on the market. And this is due to the biggest engineering problem for this project being the origin of the sensor is constantly moving in the Cartesian axis and radial, and there's a lot of noise rejection filtering required to make it a dependable and consistent product. Due to the allotted amount of time, certain concepts that were within our scope fell through, including Bluetooth transmission. We wanted to have a Android application work in tandem with the detection algorithm, but instead it was all analog. So to segue into future work, that would include the Bluetooth capabilities working with the Android application. If not, another option is assigning a PWM to the buzzer to at least have an audible distinction between different danger levels depending on the velocity of the approaching object. And there are capabilities or potential for the prototype to become more compact in its final design using a different microcontroller or eliminating the buzzer altogether. These would all be more appealing to a customer looking to buy this product. That's all.
We are a two-screened group, so glad that you have joined us. Good morning or afternoon. I'm not quite sure what the time is. We are Bright Step. This is Bright Step. This project focused on delivering a sustainable safety lighting tile to reduce slip, trip, and fall hazards. So I'm Kara Dees.
I'm Zach Rogers.
Jay. Christian.
Andrew.
And Mo. The goal of the Bright Tile Step was to create a safety solution that was not only cost effective, but low energy and renewable. To achieve the renewable aspect, piezoelectricity was chosen as the energy source. Piezoelectricity is the electric charge that is produced in certain materials like crystalline structures when a mechanical stress is applied to it.
So this project was multifaceted. The biggest challenge the group ran into on the front end was that there is no simulation tool for piezoelectricity currently. So each of the components were tested individually, which culminated into a final design. So some of these components were full bridge rectification, designing to a certain storage element, whether it was a battery or capacitor, considering components that required an external power supply, whether it was the AND gates. Sorry about that. Here, whether we needed to use this logic circuit, and whether we could support it with the power we generated from the piezoelectricity. The project determined that the piezoelectric crystals were optimal in a parallel configuration. And then the team also regarded the output voltage and some Zener diodes as 4 gap voltage drop over certain ranges, which all of these components culminated in our final design, which actually ended up implementing a specific chip.
The final design ended up utilizing piezoelectricity, as we determined that was easiest for the renewable aspect. We also chose rectification as a way to store our energy in a capacitor, which was deemed the best storage solution, and also voltage transformation in the form of a buck converter that stepped down the voltage and increased the current through the LTC 3588 chip we used, which helped attain a 3.6 constant output voltage.
So here's a quick overview of the circuit diagram from left to right. Here is where the storage capacitor is located. It is a 4.7 millifarad with a rated voltage of 35 volts. In the middle, and our main component is the LTC 3588 and the piezoelectric crystals connected to the chip. A total of 24 of them are there, not 4. And in between the LED strips and the output of the LTC 3588 is our logic circuit, which contains a pressure sensor, light sensor, and a time-based latch. So inside the LTC 3588, there is an ultra-low drop bridge rectifier with a forward voltage drop of 0.7 volts and can support up to 50 milliamps of current. The output of this goes into the storage capacitor, which is located at VN. In between the two, there is a voltage clamp here, which clamps the voltage at 20 volts and extracts any excess energy from entering the storage capacitor using this Zener diode. Here, there is 2 digital bits for a selected output voltage of either 1.8 2.5, 3.3, and 3.6 volts. Here there is a low current under voltage lockout detector which controls the buck regulator. There are two input bias circuits that control the top side P-channel MOSFET and the bottom side N-channel MOSFET. The operation of this board is as the voltage of the storage capacitor increases and goes 1.2 volts above the selected voltage here, this detector will turn on the buck regulator, which then turns on the top side P-channel MOSFET that will then ramp up the current to 250 milliamps. Sorry. That will then switch off and then turns on the N-channel MOSFET, which ramps the current down to 0 amps. Once this is done, it has transferred the energy from the input side to the output side. Once the voltage of the storage capacitor goes 200 millivolts above the selected regulated voltage, the buck regulator goes into sleep mode. And it would only turn back on when the voltage across this capacitor goes well above the regulated voltage. Thank you.
So this table here, this table here shows the charging of the capacitor, and when the voltage reaches, as Mo said, 1.2 volts above the desired output, it'll actually cleanly output the desired value. Here is what our initial design for the circuit board, or not the circuit board, sorry, the platform. We have the piezo sensors on each side, roughly shoulder width apart, so that as you're walking across it, you get the maximum pressure on the piezo sensors. We left a space in the center for all of the circuitry, and then LED lighting in the gaps above and below. And as you can see, we used, for the platform, 3 layers of plywood to create the base with a gap in the center for all the electronics, with a plexiglass top plate so that we could show the workings. We designed and 3D printed a holder to locate the sensors in the correct places on the board, and they were attached with hot glue to assist in evenly distributing pressure to the entire sensor.
3 different capacitors were tested before the decision to use a 4700 microfarad capacitor. The reason the 4700 farad capacitor was chosen was the total storage as well as the efficient discharge time. The 2 other capacitors that were chosen either had not much voltage capacity or a very quick discharge time. A discharge time around 22 seconds was achieved without a LTC board attached. These were all tested under the same conditions of max capacity, discharged through the same load. And after the capacitor was chosen, the LTC board was attached to it, which regulates the output voltage, and we were able to achieve a nearly linear discharge time of 1 whole minute under the same conditions, full charge to completely empty with the same load. Towards the end, there's a little bit of a fall off just due to the lower voltage capacity in the LTC boards working. But the discharge time was extended to nearly a minute with a consistent discharge. The LED brightness was consistent through this entire phase as well.
Here's a figure model of force over
It's
time.
hanging down, the microphone.
Here's a figure model showing force over time from a normal footstep of a 70 kilogram person. And using Raymond's sum, a force could be calculated for a given mass. And this chart is showing 4 different age groups and their average mass and the force which was calculated. And given each of these masses, every step on the platform was measured, and the increase of the voltage across the capacitor energy was calculated. And approximately 1 unit of force produces about 911 picojoules and about 25.86 microvolts on a 47 microfarad capacitor. Here's a sample data given from a slow walking rate of a 77 kilogram person, and this is showing the charging rate on a 47 microfarad capacitor, and for every step, so this would be 1 step, and for every step it's about 14 to 16 millivolts, and that's about 528 nanojoules on the capacitor. And to completely charge an 18 volt 47 microfarad capacitor, it would approximately take 1,200 steps, which would last 60 seconds of time on the LEDs.
Let's see if it'll show.
This is a quick demonstration of the
Platform.
This demonstration for
The discharge of the platform. So we'll play that one more time. So this platform has already been charged, and it is in use. So you'll see the switch activating as the person steps on it. Has anyone ever tripped or stepped on a Lego in the dark? This allows you to be able to see.
Here's the breakdown for the cost. As you can see, comparing the total, the sum is 135.24. What costs the most is the 24 pieces of piezo crystal sensors that the project used, and which is increased like 45%. Yeah, roughly around 45%. And there are a few challenges encountered with this project. The chip burned out during the testing phase, and I have to wait for the new chip coming in, which causing a delay for the final result. And then even though there's 24 piezoelectric sensors are using during the testing phase, but it would take a large amount of time and footsteps which are Angela mentioned 1,200 footsteps to generate only 60 seconds of the time. And the photo cell was testing it during the design phase and testing phase, and what happened is it will detect the lights, and when the LED is on, so it was just flickering off constantly when lights off and on.
I'll use the microphone. So our closing remarks, the LED design, or the piezoelectric design, led to a sustainable tile that we built, making it minimally power intensive. So the project determined that the parallel configuration is the best configuration for optimal output from the piezoelectric crystals. The LTC 3588 chip is a great chip. We really enjoyed using it, and it was robust for our application. And looking towards future work, we've seen monitoring of foot traffic and monitoring of voltage power generation over time. So those are other applications. You can do it using a wireless voltmeter. There are other tools that we looked into just for furthering this research. And also we want to take a second to just say thank you to Kennesaw State University, the Department of Electrical Engineering, and especially Dr. Cheryl Okayo supporting our team, and Charles Duvall over here, who is our faculty advisor. We are very grateful for all of them. Oh, and Dr. Thane, sorry.
What happened here?
I don't know how to fix that. Yeah, there we go. Thank you so much.